Alright, we're going to look at a second example. This time we'll look at a convex mirror so that we've got both cases. 5 centimeter tall object placed 11 centimeters in front of a convex mirror that has a focal length of 5 centimeters. Determine the characteristics and dimensions of the image. Again, complete the charts using a ray diagram and then the curved mirror formulas. So again, the first thing we do, put in the mirror, put the object, put the focal point and the center of curvature. Labeling the distances accordingly. 5 centimeter tall object in front of a convex mirror. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 5 high. Focal length of 5 centimeters, so the F point should be 5 centimeters from the mirror. 1, 2, 3, 4, 5. And the center of curvature should be twice as far, 6, 7, 8, 9, 10, along that principal axis. Always start with the accurate labeled information, and then we're going to draw the rays in after. So the convex mirror tends to be a little bit trickier in the fact that the focal point is behind the mirror, the center of curvature is behind the mirror. So we have to be real careful with these virtual points. And when we draw our first ray, again, I always start with the one that's parallel, but this will reflect off, but it's not going to reflect off through the focal point. We have to look at it as looking like it comes from the focal point. So I tend to draw that ray from the focal point to the mirror, and notice I draw it dashed because it's a virtual line, and then the actual reflected ray will follow along that line. So it appears to come from behind the mirror. Doesn't really, but it appears to come from behind the mirror. That's the little bit different with a concave mirror compared to the convex. The second one that I draw is going to be the one that would appear to go through the center of curvature, because that one will reflect back onto itself. So just like the other diagram, appears to come from the center of curvature, and notice it's dashed behind the mirror because it's virtual, and notice it's a double-headed arrow because it'll reflect right back along the same path. I tend to only draw these two because all you need is two for an image. And again, I drew the image dashed because it's behind the mirror, which means it's a virtual image. And if we were to list its characteristics are, it's erect, meaning in the same direction as the object, it's diminished, and it's virtual. The image that you see appears to be coming from behind the mirror, which is why everything behind the mirror is dashed, and it needs to be dashed. You get marked wrong on ray diagrams if you don't put those lines dashed. We can count out the distances for this to try to find our different distances and heights. If you count this out, it's 1, 2, 3, about 3.5 centimeters behind the mirror. Its height is about 1.7, 1.8. So we can label that on our diagram. So the distance is, this will be a negative value, negative 3.5 centimeters, and its height, because it's above the principal axis, will be 1.7 centimeters. Now if we're going to do this algebraically, let's label what we know. Since the focal point is behind the mirror, using our sign convention, virtual focal points have to have a negative distance. So our F value should be negative 5 centimeters. The distance of the object, well, that's in front of the mirror. That was 11 centimeters. The height of the object, well, that's above the principal axis. So that's 5 centimeters. And we're going to find, again, the distance of the image, the height of the image, and the magnification. Same as the last problem. So again, start with the formula. 1 over f equals 1 over distance of the object plus 1 over distance of the image. Manipulate this for the image. 1 over distance for the image equals 1 over f minus 1 over dO. Put our numbers in. Same as the last problem, you just have to be real careful with your signs. This is 1 over negative 5.0 centimeters. Subtract 1 over 11 centimeters. Be really careful when you punch this in. And again, it'll be 1 divided by 5 negative. Subtract 1 divided by 11. Reciprocal that answer. And you should get distance of the image equal to 3.4375 centimeters. Should be negative because it's behind the mirror. It's a virtual image. So if we go to 3 significant digits, it's 3.4 centimeters. And again, back to our magnification formula. HI over HO equals negative DI over DO. Put our numbers in. HI equals negative DI times HO over DO. Substitute negative distance of the image will be 3.4. Forgot my negative sign. Times HO, which will be 5 centimeters, over DO, which is 11 centimeters. This height of the image should work out to being a positive value because it is above the principal axis. Notice I forgot one of my signs in there. I had to add it after. A negative times a negative will give you a positive. And if you punch that in, you get 1.5625 centimeters. And again, if we round that, should be 1.6 centimeters. And now we just calculate the magnification. The algebra of this question is identical to the last. You just have to remember that those virtual focal points, those virtual images, have negative distances. Heights that are below the principal axis are negative. If you forget that, you will make some mistakes in your algebra. So our magnification here is going to be, again, I use HI over HO. Graphically, it'll be 1.7 centimeters over 5 centimeters. So 1.7 divided by 5 gives you 0.34 for a magnification. Again, should make sense because we do have a smaller image. And if we do this again with the algebra numbers, HI over HO and go 1.6 divided by 5 centimeters. You get 0.3125, so it's 0.31 times. Again, fairly close, but the algebra numbers are slightly more accurate. Whenever you're doing something graphically, there's always room for a little bit of error in this case. But they should give you really good characteristics. It's very easy to find characteristics from the ray diagram. It's a little harder to find characteristics algebraically. Then you have to really understand that sign convention. So I tend to draw the ray diagram just to get the characteristics down pat, then do the algebra for all my numbers. There's two examples of mirrors. One is a concave, one is a convex. Draw two rays to find your image, and then remember anything behind the mirror, the distances will be negative, the focal point will be negative, and the image will be negative. Anything in front of the mirror, you will have positive values. Any image that's below the principal axis will have a negative height. Any image above the principal axis will have a positive height. Lots of things to remember, but if you do about 10 questions or so, it'll really help.